Unit 8. Area. Page 1.
All right. I have nothing funny today. I couldn't think of anything. Thought for like 5 minutes, and I was like, no, I'm not doing it, bro. And my camera's not detected. Hold on, guys. Let me unplug my 40 different things this could be. No, that didn't work. Okay. All right, and hopefully, now that we select the camera again, we get the Ziggy Plus, which is what this camera's called. I'm not even kidding. That's not even a joke. Alrighty, and the beautiful, lovely Unit 8 review shows itself. So, guys, basically, essentially, I'm just going to do page 1 here very quickly and briefly. I do have some other stuff I have to do today, so we're going to try and get out of here before reasonable time. So I'm going to go reasonably quickly. Just feel free to slow down the video if you want to slow it down. Feel free to speed it up if I'm going too slow for you, etc. We're going to do these 3 problems, and then I will come through and help us out. Okay, let's see. I have a student at the door. Okay, and I'm back. That's so funny. You know, like, this is like Interstellar. For you guys, that was like instantaneous, but I've actually been gone for like 10 minutes working on something else. Wow. No way. It's like that planet from Interstellar. Okay, anyways, so dimension changes, baby. Whenever you change the dimension, you change the shape. Whenever you change the shape, you change the area, you change the volume, you change the perimeter, etc. How it changes exactly, though, is quite interesting. So, for example, on number 1. Now, at first, this is going to seem like common sense, but then when you get into it, you think, fascinating. So, anyways, just keep that in mind. Suppose a wall in a house is 13 feet long and 8 feet tall. If the homeowner wants to paint half of the wall, how much less paint will it take? So I guess what I should say here is, like, instead of painting the whole wall. So, like, for example, here it says 8 feet tall, 13 foot long. What am I trying to say? Wall here. And then imagine we're going to paint this wall. So, like, right now he has to paint the entire surface area, which is 8 times 13, length times width. 8 times 13 is 80, plus 24 is 104. And this is going to be square feet, so just make sure you keep that on there. So there's the original, all right? And if we add to this, if we continue, he wants to only paint half of this. So imagine that you just take, like, half of one of these lengths. Like, for example, I mean, no one would ever do this, but if I divided the wall this way, that's half, right? So maybe this is 4. So this rectangle down here, obviously, would just be 4 by 13, which is 40 plus 12. So it is 52. Does that add up? I think that adds up, right? And that ends up being exactly half of the area, obviously, because we just took half of these numbers. Okay. Anyways, so to answer this question, how much less paint will it take? Well, if we take 104 square feet minus 52 square feet, that equals 52 square feet. Very nice. Now, when I was making this problem, what I didn't think about is that you obviously, I don't think you buy paint in square feet. You buy it in gallons. So, you know, you would have to, if you were really doing this in real life, you'd have to think about, well, how many gallons of paint is this going to be? And you can determine this by just going on Home Depot's website or whatever. Like here, I wish I could show I only have a camera here. Like I can't make this screen into like a share screen like Zoom or whatever, or I would do that and we could just Google it and see, but I'm not sure. For the case of the video, let me just look it up and we'll see real quick. Because I think it makes more sense, right? You know, like how many square feet is 1 gallon of paint? Okay, and apparently Lowe's says, the Lowe's website, now let's do Sherwin-Williams. They're the pros, right? Sherwin-Williams says, if Drooping Springs will let me view this website, it doesn't like this website very much. Anywhere from 300 to 400 square feet. So let's just lowball it and say there's like 300 square feet per gallon of paint. Alrighty? 300 square feet per 1 gallon of paint. Obviously, we could find out how much that is by multiplying by 1 over 300. And so in the old calculator, 52 out of 300. Well, let's see. If you were going to use 52 out of our total 300 feet, 300 square feet, that's about 17% of 1 gallon. So we would say, like, I don't know, maybe 2/10 of a gallon. So if you go to the store, how many gallons of paint do you buy? 1. Or if they have like a little one, maybe like a quarter gallon, you could buy that as well. All right, cool. And next up, number 2. This one is quite the puzzle. So I didn't mean to make this problem this hard, but it's just a lot of steps. It's not really that difficult, but it's a lot of steps. So let's see. A garden in the shape of a semicircle, that's this shape, right, requires 50 pi, ignore the is, requires 50 pi square feet. Once constructed, the builder realized it was too large. So like, let's say, for example, it doesn't fit. Wherever he's trying to put it, it doesn't fit. He does some measurements and he determines, let's see, the diameter needs to be reduced by 6 inches. Okay? How much area will be lost in the garden? So let's say, for water drainage, it has to be a certain size for this particular garden. And he's worried that it's going to be too small after he scales it down. How could we know how much? Without having to take up the entire garden and build it again, how could we know how much? So, for example, in this particular instance, here's the garden-ish shape. And on the inside, it gets 50 pi square feet. And the only reason I left it in the exact form is just because it's easier to work with in the calculator. It doesn't really matter how it's set. Alrighty? And obviously, if we want to reduce this diameter, then we need to know what the diameter is. So to do that, let's find the radius. We know that the area of a circle is given by pi times the radius squared. So if 50 pi square feet is the area, we'll replace that with a. 50 pi being the area, pi r squared on the other side. And now check this out. On one side of the scale, we have a pi. On the other side of the scale, we have a pi. Then they weigh the same, so they just lift right off. And pi and pi cancel from either side. Really what we're doing here is dividing both sides by pi. And then our next step, we can get that 50 equals r squared. And wait a second. What have I done? Look at this, guys. What am I doing? Before I mess this up, this is my last chance. Is this the area of a semicircle? No. This is the area of a whole circle. Look at this. Unbelievable. The area of a whole circle. So to make this work, I need to take half of this area. So here, imagine plugging in a half right here. And I know it's kind of cramped. Sorry, guys. I didn't even think about that. Right, there's a half there. Whenever I was about to take the square root of 50, I thought, oh, that's odd. Okay, anyways. So half of this. And now to get our next step, it'll be 100 for r squared. So imagine, like, just as a recap, 50 square feet is only half the circle. So 50 pi square feet, I should say, 100 pi square feet is the whole circle, which is what the area formula finds. It finds in a whole circle, right? And so anyways, our radius must be 10. And this is going to be feet. Ready? This means that the diameter is 20 feet. Bam. So now that we know our diameter, let's reduce it by 6 inches. So the diameter minus 6 inches, isn't that the same as doing the radius minus 3 inches? Okay? And notice our radius is in feet. So if I want to take 10 feet and subtract 3 inches, I can't just do that. I need to know inches in feet. So let's see. How many inches or how many feet is 3 inches? Well, we'll just do 3 divided by 12. And we see that it's a quarter inch, or excuse me, a quarter foot. Alrighty? So this is 1/4 of a foot. So we'll take out 0.25 feet. Alright? Again, this is the losing 3 inches. Losing 6 inches on the diameter, that's like losing 3 inches on the radius. And we need the radius to do area. So, again, this is our 9.75 feet for the new radius. And now the new smaller circle that we're going to try to install, let's see how much area we actually lose. So the area of this new circle is going to be pi times the radius squared, which is 9.75 squared. Alrighty? That's equal to, and then here we'll see 9.75 squared times pi. Well, actually, let me leave the pi out. We'll leave our answer exact for now. That seems a little bit easier. We get 95.0625. Beautiful. And this is in square feet. And you don't have to write all these decimals every time, as long as you use all the decimals in the calculator, guys. Okay? And next up, we will quickly note... Oh, I'm sorry. And there's supposed to be a pi here. My fault, guys. I forgot my pi. 9.75 squared is 95 point this pi. And now let's see. How much did we lose? So this is an area of the whole circle. Our garden is only a half circle. So I'll take half of this to get, and then we divide by, oops, let's go up. Divide by 2 here, and we get 47.53-ish. Again, all approximate. And there's a pi there, don't forget about that. And so, how much more area did we get? Let's take the original 50 pi minus 47.53 pi. And again, I'm only writing 2 decimals, but when I go in my calculator to make sure that I get the most accurate answer, I'm going to take 50 times pi minus, and then I'm actually going to arrow up, grab this whole number before I put it back on pi. And here we get about 7.755. Okay, so what does that matter to us? That's about 7.8 feet. Square feet, I should say. Lost. Isn't that weird? So even though we only lost 6 inches on the diameter, we lose about 8 square feet in our circle. Alrighty? So I don't know. I want, of course, I would love to make this problem more in depth and like give you a contractor and requirements for these numbers to make sure that they match up. But just imagine that. All right? I can't make the problem that long. Imagine that maybe this was under or over a certain threshold for how big this new garden could be. Okay? So, for example, let's continue on. We got another one here. The support for a wall bookshelf is pictured below. So I imagined this like, you can imagine like a bookshelf. Let's see if I can draw this. I don't know if I'm going to be able to. Like imagine like a bookshelf with like a load of books just all stacked up. Okay? I imagine like this support is this piece here. You know? That like holds up the rest of the bookshelf. So this is what I'm thinking of for this shape. It's like a trapezoid. Okay? It says, a new design reduces the height by 2 inches and leaves the bases the same. How is the area and perimeter of this shape, affected by the change? Is it similar to other polygons? So first, how is the perimeter and area of this shape affected by the change? So let's look at the original. Why do we care about perimeter and area? This is related to how much product we're using. Let's say it's made of wood. How much wood do we need? That's related to its area and perimeter. So, for example, if this side's 5 and this side's 2, this height is 4. The area of this trapezoid has got to be half base 1 plus base 2 times 4 for a total of 7 times 4. Half times 4 is 2, right? So 7 times 2, which is 14. And this is going to be, I didn't write the units on here, but it is supposed to be inches. So this is inches squared for the original shape. Okay, and for the new shape, the change is that this is no longer 4. So for the new shape, for example, it's got to be 1/2 5 plus 2. The bases are still the same, and then this part is different. Half of 2 is 1, and so we simply get 7. Interesting. So, when we reduced the height by 1/2, our area also was reduced by a half. Interesting. So that is cool. And yes, that is actually the case for other polygons. If you remember back to our discussion about how dimension changes things, if one dimension is, like if you scale a shape by k, if one dimension is involved, then it changes by k, which is what we got here. If two dimensions are involved, for example, an area, then it is altered by k squared. And likewise for volume, it is altered by k cubed. That's the old notes there. Very fascinating. In any case, we also would like to know the perimeter. For this shape, the perimeter is 5, 4, 2, and 5. So these together are 10. These together are 6. All together, that's 16 inches. And I had a really good question today. A student said, how can the perimeter be more than the area? What an excellent question. How can the perimeter be more than the area? I like this. This means you're thinking, bro. In truth, it is not. Alrighty? 16 inches. You can't write anything here for 14 square inches. These two values are incomparable. They are fundamentally different. This one on the left tells you how far two things are apart, whereas this one on the right tells you how much, of an area is being used, how like spacious something is, how far you are apart. This is a distance. And on this side, it's a measure of like area. It would be like asking someone, your fence is 16 feet long. How can your yard be 1 acre? That doesn't make any sense. The acres have nothing to do with feet. They have nothing to do with feet. Like, even just because inches squared has the same unit, this measures something fundamentally different. So just keep that in mind. This is why on the test it matters so much what your units say. This answer means something fundamentally different than this answer. If the answer is 14 inches squared and you put inches, you're wrong. If the answer is 14 inches squared and you put 14, you're wrong. It has to be 14 inches squared exactly. Okay, just keep that in mind. Alrighty. And guys, the reason for that is, I know the argument is, we all know what I meant. Okay, yes, maybe we did. I know what you were supposed to mean, but how did I know you knew that? You have to show me that you know. The test is about demonstrating what you know, so just keep that in mind. Okay, for this shape, we're actually missing a side. So to find our perimeter, we'll have to go a little more in depth. Now, what I'm thinking is, a cool way to do this would be if we cut this piece into a square. We draw an altitude right here. That means this side must also be 2, and so this side is 3. And now that this side is 2, we have a right triangle, and we can use the Pythagorean theorem to find this last side. So, Pythagorean theorem states a squared plus b squared is equal to c squared. Here, a and b are replaced by 3 squared and 2 squared. And finally, our length must be the square root of 3 squared is 9 plus 2 squared is 4 for a total of 13. So let me do 9 plus 4, and then here we get root 13, which is a disgusting irrational number. But if you wanted to know what it is approximately, you could ask the calculator. It is about 3.6 inches. So, very nice. Here, 3.6 inches is the best guess. So now, for the perimeter of the new shape, we'll just total it all up. We have 5, 2, 2, and 3.6. 2, 2, and 4. 2 and 2 make 4. 4 and 5 make 9. 9 and 3.6, that's 9 and 3, which is 12. And then 0.6 hangs out for a total of 12.6 inches in the perimeter. Okay, very nice. So, now, and again, the depth of this is like the surface level of the problem. We're only in high school. We can't do an actual real math problem. But you can imagine a person who this is their job or is really an engineer, they're wondering, is it worth it? Is 14 inches squared going to lose me strength or whatever from my bookshelf, right? Stuff like that. Is it easier to screw in now? Is it easier for the user to handle or build themselves, depending on the decisions we made? This is just a tiny part of that process that we do in high school. Okay, that's the first page. Come back for the second page, gamers.